And thank you for joining me for this final presentation today. I was able to attend a lot of the sessions, and so it was great to hear both from my colleagues, but also from our customers and some of our external speakers. Today, I'm going to give some background on modern computer science technology needed to help make business automation easier and ultimately accessible to non-programmers. I'll also explain some of the technology that we have developed for our existing product and some of our research work. Finally, I'll give you my perspective on the path forward to building technology advancements to make generalized automation achievable. First, some logistics. If you have a question, please use the Q&A tab on the right and add your questions there. I'll try to answer as many questions as I can at the end of my presentation. If I don't have time to answer some questions, I will be at one of the presenter tables after my talk in the networking floor to talk to you one-on-one. First, a little bit of background, a bit about myself. Dale mentioned I'm a professor. I'm a professor of computer science at the University of San Francisco. I teach and research in the areas of operating systems, computer architecture, programming languages, and distributed systems. Fundamentally, I like to help students understand end-to-end how computer systems really work. 10 years ago, I joined SnapLogic to apply my research background to data integration. I was one of the architects behind the current cloud-based platform and lead our AI and ML efforts. Every fall semester, I sponsor USF graduate students to work on SnapLogic-related research projects. So what we're all here today, automation is key, right? And the natural question is, who can automate the enterprise? And there's a lot of debate around this, right? Traditionally, IT departments, programmers shoulder the burden of putting the technical pieces in place to implement various forms of critical business automation and maybe even non-critical. But to what degree can business users, right, the non-programmers, the non-IT workers, be self-empowered to automate processes? Low-code approaches like SnapLogic have made significant progress, but there's still a lot more work to be done. The question is, what technology and user experience is going to take low-code and no-code to the next level? To be clear, the goal here is to enable less technical users, ones who understand a business domain, to be able to create working automations. And fundamentally, a real automation is a program. Okay, we're not talking about just configuration, but a new way to actually program. A program acts on data input, makes decisions, and can detect errors. Configuration involves filling out the parameters for an existing, well-tested, purpose-built program. Programming is really about creating something new that doesn't yet exist yet. Because if you think about all the things that you might want to automate, right? No company can provide purpose-built solutions for every possible automation scenario, right? So like anything that is a program, it needs not only to be created, but tested and debugged. So I'm going to give a little background in the some of the fundamental areas of computer science that have been ongoing for several years now. One area that computer science researchers have worked on is something called program synthesis. And the basic idea here is it's programs that write programs. This is a hard, unsolved in the general sense problem. It's considered one of the holy grails of computer science research. The goal is to allow less technical non-programmers to specify and construct working code. It also has the potential to help expert developers create first draft code or mundane code. So why is this problem so difficult? To set the stage, let's consider an example. I'm proposing a new type of digital assistant that I'm calling Ally, sort of my Alexa Siri combination here. So Ally's not your typical digital assistant. It can be instructed to generate working programs. And this is different than what we can do with digital assistants today, like set timers or add events to your calendar or send a text message. So let's consider an example. Let's say I wanted to have Allie construct a program that does the following. Hey, Allie, every 10 minutes, record the current outside temperature. If the average of 6 consecutive readings exceeds 80, send me a text message. So this sounds pretty good. The objective makes sense. If you said this to a programmer, they would likely be able to implement working code to achieve this goal. Now, they could come back 2 weeks later with implementation, however, only asking lots of questions to resolve details and ambiguity. But we want to do this automatically and instantly without a programmer, or at least a conventional programmer. The problem with this type of natural language intent is that's missing lots of details to build a working program. So I'm going to pause for a moment. Can you think of some, just in your head, sort of conceptualize, I realize we have a range of folks out in the audience today. What's missing here to realize this? If you're a programmer, what's missing, right? All right, hopefully you've thought of at least one or two. So, and I'm sure some of you have come up with ones that are not on this list, but there's all kinds of things that either are assumed or need to be determined, or ambiguity that needs to be clarified. When to start this program, right? When to end it, where to get readings, right? Is there a sensor that you can talk to, right? What's that device? Where to store the readings, right? If we, do I need a database, right? Where's that database? Does it have credentials? And so on, and so on, and so on, right? What operating system? Where is it going to live? In the cloud? Is it in a Raspberry Pi in Craig Stewart's home, right? Who knows? Where is it? Okay. So my hope here is the small exercise is to get us on the same page of the magnitude of the problem in a general sense. So in the area of program synthesis, there's two big challenges. The first is capturing user intent. So researchers have tried and explored different ways to allow users to specify what they want to achieve without actually writing code. And these have spanned a range of different types of modalities. There's been approaches in what's called formal specification, which is really maybe more like mathematics or more like a notation that is constrained to describe a problem. These were, baby steps, right? And these forms of formal specification, while they allowed us to make progress, sometimes these could be just as difficult to write as the code itself. As we saw earlier, there's all types of forms of informal specification, right? Things like speech or written English. And as we have elaborated, these can lack details needed for synthesis. Another interesting area is that's been tried and used successfully in some areas is programming by example. And that is instead of the end user writing code, right, or specifying code, what they do is they give examples of the possible input and desired output. And providing these input-output pairs, they provide examples which then can be generalized, and then that results in code that can be applied to new variations of data that look like some of the examples. So intent is one problem. The other problem, as you can imagine, is what I'm calling here the program search space. But basically, this is what possibly can we generate? And for a moment, the way the computer scientists think about this problem is not like going from zero to constructing one of many programs. One way to think about it is, well, what if we could enumerate all possible programs, right? What if we could somehow write, or maybe even let's reduce it to all possible useful programs, right? And if we were able to do that, right? Then we think about the problem of matching the intent to finding or searching a suitable matching program that achieves that goal. Now, in this general sense, that's not entirely possible, but it does help us make progress and think about the problem, which I'll explain in a moment how that comes about. So what are some possible things that we can do to make progress? Well, we can, on the intent side, we can limit vocabulary or the types of objects and things that the user has to specify. That is implying that we're going to require some education on the user, but perhaps if we do that in a natural language way, it will still be, easier than writing code itself. We need to provide context. We need to provide a space in which the user doesn't have too many possibilities, but have enough flexibility to achieve their goals. We can also limit the target programming language. So amongst researchers in this area, there's kind of two mindsets out there. One is what I would call pessimistic, that as I've described the problem, it is a really hard problem, and real code requires too much detail. This idea that I'm going to say to a computer, I would like a new operating system that supports, text files and audio files, and out comes a working operating system. That's pretty far off. But there is an optimistic view, and I'll share some of my views as well, that that if we constrain the space, right, constrain what the user has to supply and can supply, and this is key, and I'll come back to this, and if we can more naturally support iteration, that is, I have to tell my students that when they're learning computer programming, right, they're not spending most of their time writing code, right? They're spending most of their time debugging code or shaping that code to get it to do what they actually want it to do, right? And in these low-code environments, we need to embrace this, because this is part of what a non-technical user is still going to have to do. They're still going to have to iterate on their specification, iterate on what they want to achieve. So there are more reasons for hope. Obviously, there's continued work in academia. Increasingly, machine learning has been applied. We've used it as well, which I'll mention in a bit. And then another thing I'd like to point out is something that didn't exist 20 years ago, which is really an exciting time for me to be at SnapLogic, is a cloud-based programming platform like SnapLogic has now enabled, as you've heard earlier, hundreds of companies to write thousands and millions of these pipelines that we can look at and understand what they've done. We can understand the intent and what the purpose of these are. And we can generalize that, and we can construct a corpus of existing solutions that can serve as examples. And this can help with that search space problem that I mentioned earlier. So I just want to dive into a couple of sort of milestones that we have made in the past in the product, and then also talk a little bit about some of our research. One of them one of our earliest attempts and successful attempts at bringing ML to the product is what we call the Iris Integration Assistant. It's a form of Snap recommendation. We used machine learning to construct a model that as a user is developing a pipeline, we can pretty accurately predict, have 90% likelihood that we can understand or know the next 5 snaps that you might need to continue that pipeline. The way to think about this is very similar to like in Gmail now, if you're typing ahead and you get a grayed out sentence completion, right? Google is sort of anticipating what you are going to want to type next. And this is very similar to that technology, but we've applied it to pipelines. And this is used all the time by our users in the product today. Another milestone that we made is something we call the pipeline solver. Now, this falls under a feature that we call pipeline suggest. That is, we have the ability to suggest pipelines, and suggested pipelines can, the way this works is a user provides some pieces of a pipeline, maybe the endpoints, maybe an intermediate snap that does some sort of transformation. And then we can go and see, oh, did you build something like this previously? Or did somebody in your organization build something like this previously? And then we can give you constructed examples of those. But there's actually another bit of technology in this in which we're actually generalizing and constructing wholly new pipelines that have never been constructed before. And this is really useful in the example where you don't have, maybe you're just starting, right? And you don't have a bunch of existing pipelines. So this would let you get some starting points or see the types of things that are possible to do with pipelines that maybe you didn't think of, because we have 500 snaps. There's a huge number of combinations. On the research side, something that we've worked on is a variation of programming by example. Now, this is getting into the data and into the shape of data, JSON data to be specific. And here's an example where what you can do is, on the left, we have an input document. And on the right, we have the desired variation of that input document. In particular, what this is saying, hey, is I want to add an index field to each of these array elements in this output JSON document. And so what the experimental system that we built allows you to give this input-output pair, and then we can generate in the bottom of the slide this JavaScript expression which can perform that transformation. Now, this is a work in progress. It's a research effort. It's not something in the product today, but it's the type of thing that we have worked on and are continuing to work on. All right. At the top of my presentation, I mentioned two other technologies, visual programming and NLP. Let's talk about visual programming just for a moment. So visual programming in various forms has been around for a while, SnapLogic included. What has become really popular today, especially for introductory computer science, are the so-called blocks languages, which maybe you've seen or heard of, Scratch and App Inventor. And these are, in fact, these are languages now that are regularly used in both as a general education course for non-computer scientists to get familiar with computer programming, but also, like, for example, our CS1 course is taught in Python and our CS2 course is taught in Java. But for students who have never experienced any programming before, we have a CS0 course, which is taught in one of these blocks languages. And why are these useful? And it's because they allow tactile interaction immediately, right? You have things that you can select from, you can drag and drop, you can connect them, you can try things out, you can see results, and you're not intimidated by typing out free-form text in a text editor, right? Or a source code editor. Now, if you look at the top example, this is really no different than code. It's just kind of got some nice colors, and when you use these things, it's kind of fun, right? They snap together, kind of like like the SnapLogic interface does, but it's still fundamentally code. But we found that it increases engagement, right? Because it is tactile, it is interactive. The blocks languages are more like a traditional or conventional, a visual representation of a conventional programming language. There's data flow based languages, and that is the category that SnapLogic it is. You think about these pipelines of, on the left hand side, data's coming in, and then it's flowing through these various snaps that are doing different types of transformations or queries and whatnot, and then ultimately ending up at some destination. We've, as alluded to earlier today, we're also working on flowchart-based languages, which are more of a step-oriented mode, like what you would expect if you've ever built or seen or tried to work with a flowchart, which is in the past usually used for diagramming, but now we're actually trying to allow the flowchart to be the specification for the actions to take place. Again, very tactile and interactive. The goal is engagement, limited text editing, and then hopefully guidance to achieve your goal. All right, so natural language processing, as I'm sure everybody knows, this or NLP has seen rapid advancements. The deep learning has really helped with speech to text, right? Alexa and Siri are very much able to take your speech, right, and convert that into text. Now that's one part of it, right? But the other part is, okay, now that we have that text, how do we go from that text to meaning, right? How do we understand context? How do we understand intent? How do we English can be very ambiguous. How do we disambiguate? And this requires lots of other types of machine learning models. The part that we're interested in, right, is how can we take natural language and go to code? There's not a lot of successful work on this, so this is sort of a new area. I led a group of data scientists from USF, and we gave this a try. What we did is we constructed an NLP input where you could either speak or type out in English what you want a pipeline to do, okay? So this example here, read a CSV file from S3, filter the age of customers, and write into a JSON format into my S3 bucket, okay? So we did some experiments with this, and for some descriptions, it worked extremely well, right? You would be like, oh, that's great. That's exactly the initial starting point I want in the pipeline. But when it failed, the results were pretty far off the mark. This is a problem you see in all digital assistants today. It either works or it doesn't work. There's not a lot of gray area where it sort of works or it works well enough, right? This is also like call centers, right? Immediate frustration if you're dealing with these automated call centers that are interpreting your spoken English, and pretty much all you're really trying to do is how to navigate it to get to a human that you can talk to, because as soon as it fails bad, and you don't want anything more to do with it. But we learned a lot, and we kind of learned some of our limits. We learned how to use our corpus of existing pipelines, which was a great exercise. I want to conclude my talk with sort of my thoughts on a vision forward and how to think about taking this low code, sort of more informal intent to achieve working programs or working automations. So the key points are, this is all about enabling the less technical user to program in a general way, which in the general sense is a very hard problem. SnapLogic and platforms like SnapLogic that are low code have made lots of progress. We're very happy with what the types of things and the types of pipelines that our customers have been able to create with our platform. However, there's fundamental problems that I hope I've illuminated that we need to understand, and technologies that we need to better harness. That is, a lot of the great breakthroughs in combination in computer science are the strategic and careful combinations of multiple technologies in a particular way to overcome a problem. So my view is we need the right combination of visual programming and NLP to capture intent. But it has to be integrated in a way that allows the user to see the intermediate results of how we've interpreted that intent, and then use again, in this iterative fashion, use NLP, visual programming NLP, to refine, right? Just like I was talking about earlier, like 90% of the time, programmers are not writing code, right? They're debugging code. There's going to be a similar type of breakdown here, right? The initial thing is not the final thing. It's how do we revise it to get to that working automation. So we need to embrace iterative nature of program development and enable the user to guide and direct technical development through tactile interaction in natural language. We've made progress toward this goal in our product today and have several research efforts in progress, and we are putting these together to deliver the next generation of programming systems. Come back and watch our progress. We constantly roll out new things in the product, and hopefully we'll get some more of these research efforts into the product in a very short time. I appreciate your time, and I will take questions and go over and look at the questions now if there are any. Oh, Dale, did you want to help me?
Yeah, no, that's what I was doing, mate. There's a couple I think might be useful for you. If we use a constrained language to reduce the program search space, doesn't that lead to a platform that is less capable? How do you balance those considerations?
Yeah, that's a great question. So, to be honest, it is a balancing act, right? It's and this is something that some of the people I work with closely at SnapLogic, like Mark Gibbs, will tell you, we're constantly trying to find that sweet spot, right? The sweet spot of how do we make it complex enough so that it's usable, but not too complex that it's too complicated or too difficult to either allow the user to interact or to specify that intent. And I think that leads to another question is in the short term, I don't see replacing conventional programming in a general way. I don't see replacing pipeline building like we do today, which provides another level of abstraction, but it also provides lots of sophistication. So you can do lots of things with that. We're looking at yet another higher level. And as you go up the levels, at least initially, yes, the types of things that you can do will be constrained, but we're hoping that it's going to be wide enough that it will satisfy and achieve a lot of the goals that business users want to achieve.
One more that I saw come in, we'll get to. At which success threshold do you decide to put a new ML-based AI capability into the platform?
Let's see. That's a good question. I wouldn't say we have any formal process or any sort of definitive metrics, because a lot of the stuff that we've done has been, very, especially the integration assistant early on. It started off as a research project. We had some goals in mind. We demonstrated some early success, and once it, I guess, crossed this subjective threshold of apparent usability or potential for improved usability, is when we gave it a try. We are working towards trying to expose these things in a more controlled way so that we can get user feedback on some of these experimental ML approaches, rather than sort of just doing it on our side and then showing it as a feature. So I would say the process is still somewhat ad hoc in how we're approaching it, and that we don't have a definitive, quantitative way to specify when, something that's, at least on the ML side, that we've developed and when we make the call to put that into the product.
Okay, there's one more, Greg, that I think we'll just go through. How often are you able to reuse your integrations? Is there a way you organize and distribute them?
There's probably lots of ways to interpret reuse. I'll try to interpret that as, if one of our customers has developed something sophisticated to achieve some type of integration or automation, is that reusable in a sense to other customers? Now, we have to be very careful here, right? We're sensitive to, we're very careful about not exposing any sensitive or company-specific data. So when we do these things, it's all anonymized and it's all generalized. I would say we haven't yet tried to fully reuse. What we've tried to do is learn, and that's what we've done, like with Snap recommendations and then with the pipeline solver. What we've tried to do is we've tried to learn from these existing pipelines, but we haven't yet expose them as a reusable, tried to discover fully reusable pipelines and expose them to other users. I'm not sure if that's exactly what the question was getting at, but that's under that interpretation. There's my answer.
That's a good interpretation, Greg. Don't worry. Hey, listen, thank you so much for your time. It's always good to hear you talk and the future and some of that visionary thinking. We really appreciate it. We'll make this available to everyone afterwards. So if you wouldn't mind stop sharing, I will close us out for this marathon virtual summit. Thank you very much, mate. And you can, thank you, Greg. Appreciate it.
Thank you.